Hi everyone. In this video, we will continue our introduction to measure theory. We'll begin by looking at a very specific sigma algebra called the Borel sigma algebra. And then we will begin to define the Lebesgue outer measure as a sort of introduction to the Lebesgue measure, which we will define in several videos from now. So to begin, recall from last time we discussed sigma algebra. So a sigma algebra was a collection of subsets of R, which were closed under countable unions and complements. So in this video, we want to start by looking at the Borel sigma algebra. This is denoted with sort of this script B of R. And it is the smallest sigma algebra containing all of the open sets of R. And elements of this sigma algebra are called Borel sets. Now, we can start by simply sort of thinking about what are some Borel sets. So certainly all open sets must be Borel sets, right? That's sort of the definition here, right? The Borel sigma algebra certainly contains all of the open sets. Okay. Now, from this, this just sort of comes out of the definition. So we can start thinking about, okay, what happens if I take sort of the complements and countable unions of these things? So if I take a complement of an open set, I get a closed set. So all closed sets are Borel sets. And then I can take unions of open sets. Okay. It actually turns out if you've taken topology, the countable union of open sets is also open. So that actually doesn't really give you anything new. Okay, that just gives you more open sets. But now I have closed sets, right? And I can also take complements of things. So I can think about taking then sort of a next level. Let me take, I can certainly take countable unions of closed sets. Okay. And if I also sort of think about, I can take now complements, right, of these things, sort of both of these, which would, those complements would then become intersections of, so the complement of this would give me, so let's sort of, the next thing we would get would be, goodness, a countable intersection. So if I took a complement of sets of this form, I would get countable intersections of closed sets. And then if I took a complement of this, I would get intersections of open sets, countable intersections. Now, probably not surprising, okay? Remember, these countable unions of open sets were just open sets. So their complements, which are countable intersections of closed sets, are just complements of open sets, which are closed sets. Again, if you took a course in topology, you probably talked about the fact that a countable intersection of closed sets is closed. Okay. Now, for these two, countable unions, or at most countable unions of closed sets, so these could be finite or countable unions of closed sets, they are not, well, finite unions of closed sets are closed, but countable unions are not necessarily closed. So when we extend this to countable sets, we actually get a new sort of special group of sets. These are actually called F sigma sets. these countable intersections, so a finite intersection of open sets is open, but a countable intersection of open sets is not necessarily open. These are called G delta sets. Now, these names aren't particularly important, but what I want to emphasize is that once you have these sets, you can again start taking countable unions and intersections, and you get more Borel sets. So these Borel sets, they certainly open and close sets, right? Those are Borel sets. But you also get this sort of hierarchy of Borel sets where you build these F sigma sets and these G delta sets. Then for the F sigma sets, you could start taking countable intersections of those. So you would get what are called F sigma delta sets. For the G delta sets, you could start taking countable unions. Those would give you G delta sigma sets. And then you can keep sort of alternating these things. So you can get these very sort of complex types of sets just by starting with the Borel, the sigma algebra that contains all of the open sets. Okay. Now, what I want to note here about this Borel sigma algebra, certainly if you take the set of all open sets, you have that the Borel sigma algebra is a subset of that, right? And we can already see, right, this is a proper subset, right? These cannot be equal to one another, okay? Now, the question then becomes, how does this relate? I mean, one possibility is that maybe everything is a Borel set, right? Maybe this sort of generates all the possible subsets of R. It does not, okay? So there are certainly sets which, there are certainly subsets of R which are not Borel sets, okay? And then I think a reasonable question to ask is, well, wait, why on earth are we even talking about this? I mean, other than maybe this is just an example of a sigma algebra, why do we care about this? Well, I guess one way to think about this is eventually our goal is going to be able to measure some subsets of R, okay? Now, if we think about open sets, like open sets in R, for example, can always be built as countable unions of intervals, okay? So this is sort of like, you know, I'll say like that's intervals plus, right? But it's really just sort of like open intervals. Those are easy to measure. We wouldn't really do a lot of measure theory if we were just working with this, okay? And similarly, even if you tried to say open and closed sets and maybe like those would all be sort of easy to measure. And so this has really nice topological structure, but it just sort of doesn't contain a lot of interesting stuff in terms of measuring things. On the other hand, the power set seemingly contains too much stuff, right? I mean, contains everything, every possible subset of R. And as we sort of alluded to, that's probably going to be too much stuff, like to try and measure everything in that set. So one answer of why we sort of start caring about this is that this is some sort of intermediate set, right? It's sort of a bit more than just the topologically necessary things, but not quite as much as everything. So it's one way to think of it is it's the nice topological stuff, the open sets and the closed sets, plus these other sort of weirder things, these F sigma sets, these G delta sets, F sigma delta sets, G delta sigma sets, and then again you can keep building these. So it's sort of a bit more than just the open sets, but not quite as much as this. So it's a good place to start thinking about a collection of sets that might be measurable. Now, it's going to turn out that this is actually a subset of all of the sets that we can measure. So this is actually not the set of all measurable subsets of R. That set lives somewhere between these two. But we'll discuss that more when we get there. But this is a really good place to start, where we can still sort of get our hands on some of the properties of the sets, but not having to deal with everything. All right. So what we want to do today is we really want to start then to define some notion of a measure. Now we're going to start by defining something called the Lebesgue outer measure. Now it's probably not going to be surprising that we're actually going to use this to fully define the Lebesgue measure later on, but we'll need to first be a little careful about what's going on with outer measure before we're able to define what the actual Lebesgue measure is. And it's going to turn out that a lot of this work will be useful also when we formally define the Lebesgue measure. All right, so before we can define the outer measure here, I want to just sort of recall some things. We've seen some of this before. Some of it's just providing some notation to things you already know. So the first thing I want to talk about is the notion of an open cover. Now, we talked about open covers back in 5610. And there we said that an open cover was a collection of open sets whose union contained some other set that was the set it was covering. Now, we're going to take a slightly different definition, though totally equivalent, of an open cover here, which is instead of saying that it's a collection of open sets, we're actually going to require those sets to be intervals. Now, every open set can be written as a countable union of open intervals. So these end up being equivalent. But for our purposes in 5620, as we were talking about this, we actually want to restrict ourselves to open covers that are collections of open intervals. So a collection of open intervals covers a set E if E is contained in the union of the open intervals IN. Okay. And again, since all of those intervals are open, this will be an open cover. So this is this definition seems maybe more restrictive, right? Because you're requiring these things to be intervals. But in fact, it certainly, if you have a collection of open intervals, that will certainly give you an open cover under the 5610 definition. Under the 5610 definition, if you have an open cover, which is just a collection of open sets, not necessarily intervals, then you can write each of those sets as a countable union of open intervals, and then you actually end up with a cover that's purely open intervals. So again, this is really some topology going on in the background. What I want to emphasize here is that now when we're talking about open covers, we're talking about covers of open intervals, not just open sets. Okay, and the reason we really want to work with intervals is it's really easy to measure an interval, right? Or at least, right, our notion of what a measure should be, right, is one in which the measure of an interval is just its length, right? So we're going to just define the length of an open interval, right? The open interval AB is length, which we'll define, we'll call this L. L of I is just B minus A, right? Upper endpoint minus lower endpoint. Right? So again, this is nothing earth-shattering, but just that's what this script L means when you see it. All right. So with all that in mind, we can define the Lebesgue outer measure of a set. So for any subset of R, we define the Lebesgue outer measure, which we'll call mu star of E, to be mu star of E is equal to the infimum of the sums of the lengths of open covers of E. So again, here we have this infimum. The infimum is over all open covers of E. And for each open cover, right, you're taking the infimum of the sums of the lengths of each interval, of each open interval in that open cover. Okay. Now, almost immediately out of this definition, you can start to get some properties. Okay. So one of the first things we get is that this Lebesgue outer measure is monotone. Okay, so if A is a subset of B, then any open cover of B is also an open cover of A, and therefore the outer measure of A must be less than or equal to the outer measure of B. Okay, I'm going to put this here. This isn't like, I mean, if I was going to write out a full proof, I might put another sentence or two in here. But this is actually a property we're going to use quite a bit. So I just wanted to go ahead and put this up here as sort of a property of the Lebesgue outer measure. And notice that, I mean, again, this isn't one of the things we wrote down on our wish list, but this seems like a reasonable thing you would expect, right? If A is a subset of B, then surely the measure of A, it certainly shouldn't be bigger than the measure of B, right? So this seems like a reasonable thing we would expect a measure to have, even though it's not something we formally wrote down. Okay. Now, again, to just help understand how this definition is working, right? So imagine, I have my real number line sitting here, okay, and I have some set, that I want to measure, and this set, it says could be any subset of R, so it could be any sort of weird looking set, and even this isn't particularly odd. You can imagine some sort of like limit point thing going on here, like, okay. But I want to measure this. And so the idea is if this is my set E in green here, okay, then what I'm going to do is I'm going to start by taking an open cover of this. Now, I could take an open cover that's like a really, right, if I think about sort of this orange set here as being an open cover, this is a pretty uh, bad open cover. I mean, bad in the sense of it does contain all of E, but it contains a lot of other stuff too, right? And so I have like I1 and I2 here, right? And so one way to think of it is, well, I'm going to essentially approximate this by open intervals, right? And so I just take the length of I1 plus the length of I2. That sort of gives me some sort of approximation of the length, in sort of air quotes, the length of E, right? But of course, I realize this is not very good, right? It covers a lot of things. So what I do is I keep repeating this. For every possible open cover, I do this, right? Now, it makes sense, right, that whatever length I come up with here, this has got to sort of be an overestimate in a way, right? Because this is an open cover of E. So it's going to contain things possibly that aren't in E, right? So what I do is I take every possible open cover, I compute the lengths of all the intervals in that open cover and add them all together. And then I look at all of those sums that I've taken and I say, well, what's the infimum of all of those? So in some ways, it's like asking, what's the minimal thing I was able to cover this with? Now, of course, it's an infimum, so that doesn't mean that whatever our outer measure is actually something that is realized, right? It might not actually, the outer measure may never be realized by taking a particular open cover and summing all of its lengths. But the least upper bound of all of those things is what turns out to be the outer measure. Okay. So again, one way to think about this and why it's called a really outer measure, right, is you're measuring the set, but sort of from the outside, you're covering it up with things. Now, historically, there were folks who thought about maybe trying to think about something like an inner measure as well. I will say that you run into some problems trying to do that, well, it just turns out that we don't need to worry quite so much about that. But so you might wonder though if there's an outer measure with such thing as an inner measure. I mean, people did try to sort of think along those lines, but it sort of turns out not to be the path that we want to pursue in defining measure here. All right. So let's look at a couple of examples here. The first thing I just want to show is I want to show the outer measure of a set that just contains a single point. Right? I want to show that the outer measure of that set is 0. Okay. So, well, let's see. How do we do this? Okay. Well, here, what I'm going to do is I'm going to first just create some open cover of this single point. Okay. So I'm going to let I sub n be sorry, let me call this I sub k. This is going to be a minus 1 over k to a plus 1 over k. Now notice, oops, that has run into the, all right, put that up a little high. We'll let I sub k be a minus 1 over k to a plus 1 over k. So what I want you to see here is that for each fixed k, we get an open cover of the set A. Okay. So if I know, so I know the definition of mu star of A, right, by definition is the infimum over all open covers of the sums of the lengths of those open covers. Now, in this case, my open cover is just a single interval. I don't need multiple intervals to cover this. But I'm also not looking at every open cover, right? I could take an open cover which has multiple intervals, but I don't need to, okay? But the definition says I should look over all open covers. So what I'm actually going to do is I'm going to say, well, I'm not doing that, okay? I'm going to look at this over an infimum of some particular class of open covers. So I'm taking an infimum over a smaller set. When I take an infimum over a smaller set, which is some subset of this set of all open covers, that could make my infimum larger, right? So this actual Lebesgue outer measure is actually less than or equal to the infimum overall k of, now in this case, what is the sum of the lengths of my intervals? Well, there's only one interval in each of my open covers here, right? And the length of each of these open covers is just 2k, or sorry, 2 over k. But what is the infimum over all natural numbers k of 2 over k? Well, the limit of this as k goes to 0 is 0. This infimum is 0. Right? This is decreasing and going to 0, so its infimum is 0. So what does that tell me? This tells me that the outer measure of A is less than or equal to 0. But also, if I look here at this piece, right, each of these, the length of an interval is always strictly positive. Okay. And so I have an infimum of things, all of which are positive. This infimum must always be greater than or equal to 0. So my outer measure is always greater than or equal to 0. So now just by knowing that this also has to be less than or equal to 0, I get that the outer measure, oh, and that's not, I'm not calling that set A, it's the single point A. So we get the outer measure of the single point A is 0. Now, in some ways this makes sense, right? In some ways this is like a degenerate interval, right? It's an interval from A to A, right? So it maybe not surprising that this is 0, but it does fall out here of the definition. Okay. So, all right, great, that works. But I don't know, I'm not super excited by that. So let's see if we can work on something a bit more complicated. So now I want to prove that the outer measure of the rational numbers is 0. And now this maybe seems a little surprising or counterintuitive because we're really starting to hone in on what is this outer measure, what is it actually measuring, right? If our goal is to say something about the size of a set, outer measure is going to tell us something about that, but it sort of works in conjunction with other notions we may have, and in some ways it's different. So one way, for example, to think about the size of a set, of any set, is just to think about its cardinality, right? So certainly when I think about Q versus R, right? One way to think about this is, right, that this is uncountable, or sorry, Q is countable. whereas R is uncountable. Okay. Another way to sort of think about these is, well, Q is a subset of R, right? And then another way to think about these is to try and think of them in terms of their measure. Now, we haven't talked about what the measure of all of R is. Maybe it's not surprising. In some ways, you can think of R as an interval from minus infinity to infinity. So maybe it's not surprising that the outer measure turns out to be infinity. But, you know, it's just another way to think about comparing these, right? Now, right, what's interesting is that all of these do sort of suggest that Q is smaller than R, but some of them tell you this in different ways, or they sort of give you different gradations of this. So when we talk about size or content of a set, there really are these competing notions, but you really shouldn't think of them as competing, right? It's not that one is the best, it's just that they give us different pieces of information. All right, so we want to show the outer measure of the rational numbers is 0. And we're going to do this in sort of a similar way to before, okay? Which is we're going to look at a particular set of open covers. Okay, but the way we're going to do this here is we're going to say, give me any epsilon you want. So for each epsilon or every epsilon greater than 0, we can define the sets IN. So I'm going to define IN to be the interval Q sub n minus epsilon over 2 to the n plus 2, comma, Q sub n plus epsilon over 2 to the n plus 2. Okay. And so your first question should be, what on earth is Qn? So where Qn is some enumeration of Q. Now, what does that mean? So remember, the rational numbers are countable. And what does that mean? That means you can create a bijection between the natural numbers and the rational numbers. So, and in fact, you can create many bijections, right? So take some bijection between the natural numbers and the rational numbers. That basically gives you a way then, look at what the natural number 1 gets mapped to. What rational number does it get mapped to? What rational number does 2 map to? So Q sub 1 is just the rational number that 1 gets mapped to. Q sub 2 is just a rational number that 2 gets mapped to. So on and so on and so on. So you get this enumeration. It's a way of saying, okay, I have this countable set of things, and this is number 1, and this is number 2, and this is number 3, number 4, number 5, so on and so on and so on. Okay. So, but notice, so what we're doing is we're basically listing out, right, our rational numbers. And then what I'm doing here is around each rational number, I'm placing an interval, right, an open interval that's centered at that rational number, but the lengths of them are getting cut in half each time. Okay. So the important thing here is that the union of all of these INs over the naturals contains all of the rational numbers. How do I know that? Well, each one of these intervals covers up one of the rational numbers, right? All right. So this is an open cover of Q. All right. So then what can I say then about the outer measure of Q? Okay. Well, by definition, that's the infimum over, and actually, sorry, I need to call these not IN. We'll call these sets KN, capital KN. Okay, and so this is capital KN. Okay. So if I take the infimum, and the reason I don't want to call these i's is that I shows up in the definition. So if I look at the infimum over all open covers, the notation here is just a little messy, of the sums of the lengths of the INs. Okay, well now we're looking at a particular open cover. So the infimum over all of them is less than or equal to any particular one. So this is less than or equal to the sum in the natural numbers of the lengths of the KNs. Well, what's the length of each of these intervals? Each of these intervals, so from Qn you go to the right by epsilon over 2 to the n plus 2, to the left epsilon over 2 to the n plus 2. So the total length of that interval then is 2 times epsilon over 2 to the n plus 2, which is just epsilon over 2 to the n plus 1. Okay, so that's the length of each of the KNs. But now you can sum these up. This is just pull the epsilon out of the sum. This is the sum 1 over 2 to the n plus 1. And again, that's really going from n equals 1 to infinity. This is a geometric series, which sums to 1/2. And so we just end up with epsilon over 2, right? So what do we have here? We have that the outer measure of the rational numbers is less than or equal to epsilon over 2. Okay. So we have the outer measure of the rationals is less than or equal to epsilon over 2. And epsilon over 2, right, is strictly less than epsilon, right? And this holds for every epsilon greater than 0, right? Because I realize I can do this for every epsilon greater than 0, right? Well, if the outer measure of Q, and I should also remind us that this is also greater than or equal to 0. So I have the outer measure of Q is between 0 and epsilon for every epsilon greater than 0. So it must be that the outer measure itself is equal to 0. All right. So again, we see this sort of progression here. We first showed that a single point had outer measure 0. Now we're seeing that all the rational numbers have outer measure 0. And note that this proof doesn't actually use any facts about the rational numbers other than the fact that they are countable. Okay, so you could actually repeat this proof and replace Q with any countable set, and the proof will still work. So actually, very quickly, you can extend this to say that every countable set has Lebesgue outer measure 0. Now, we'll also see that as a consequence of some other theorems we're going to prove in the next video. But it's just worth noting here that we actually do have a proof as well, right? We can very easily adapt this proof, I should say, to prove that every countable set has Lebesgue outer measure 0. All right, so we're starting to sort of, get our hands on what this outer measure thing is. It might be time to go back to that wish list and start to think then about, okay, what is this outer measure thing like? What does it give us from our wish list? Well, remember that our wish list, we wanted to find some measure, mu, that assigns a size to subsets of R, and we wanted to satisfy these 4 properties. Now, what I want to do is sort of keep track as we go along here. Okay, what if our mu instead is mu star, that Lebesgue outer measure? Which of these do we actually get? Okay. Well, for each interval I, we'd like the measure of that to be the length. Now, we haven't proven that, but you start to feel like, well, this was built out of that. Yeah, we're going to get that first property. Okay. What about translation invariance? Well, again, this is built out of things about intervals, right? And the lengths of intervals are translation invariant, right? So I sort of feel like this ought to work too. Okay. Now, this one is harder to see, but it actually turns out that as stated, we will not get this property. Okay. The last piece, we essentially have, you notice that we define the outer measure for every subset of mu. So, sorry, I should say, let's leave a question mark there, because maybe seemingly that will work, but we may run into some issues. So let's leave a question mark there for the time being. This was defined, right, for all of these things, but notice that we're not going to get this. So what we're actually going to do, we are actually going to show that for the Lebesgue outer measure, you don't get this, but if you replace that equality with a less than or equal to, you actually get that. And that's called countable subadditivity. Okay. These other things we still need to prove. Okay. We will do that in the next video. In the next video, we want to prove both of these. We want to prove the countable subadditivity. And then what we really want to do is say, well, I don't care so much about being able to measure every subset of R. I might really like this to be additivity. So what restrictions do I need to make to my sets that I'm measuring in order to ensure that I actually get countable additivity here? Okay, so what we'll see is that one such set that will give us countable additivity, right, is to one way we can get countable additivity is to restrict ourselves to a certain subclass of sets of R. Okay, so in the next video, we're going to continue examining this Lebesgue outer measure to see how we get this first and second properties. Despite my sort of maybe hand-wavy justification for these things being based on intervals, it's actually a little technical to prove some of the details. So we will step through those details. We'll also prove this countable subadditivity. From there, we'll then begin to sort of try to massage this then from this Lebesgue outer measure to looking specifically at the Lebesgue measure. It turns out that we're going to do that by just restricting the Lebesgue outer measure to a certain subclass of sets. So we'll say for sets that satisfy this particular property, their Lebesgue measure is just the Lebesgue outer measure. But we'll need to do a bit more work, and working through some of these proofs will help us understand what sort of the right criteria are that we want to restrict our measurable sets to. So we will work on all of that beginning in the next video.